Good day, everyone. We are the Group 3 from ME 3105, and we are here to present all about ceramics. Before we begin, we will start with a simple icebreaker game. We are highly encouraging our classmates to participate in this game by typing their answers in the chat box below. So let's begin. First word. This is the primary material used in ceramics. Our first word is clay. Next word. The second word. This is used for shaping and forming ceramic objects. This is pottery wheel. Next word. This is a durable type of ceramic, often used for functional wear. This is called stoneware. Next word. This is a high-fired, translucent, and durable ceramic. Our word is porcelain. Next word. Our last but not the least word is, this is a porous, low-fired ceramic, often used in decorative wear. This is called earthenware. Now we are done with our icebreaker. We will now proceed with the main discussion.
Let's talk about ceramics, a fascinating class of materials that has been around us for like thousands of years. Unlike metals or organic materials, ceramics has their own unique set of properties that make them incredibly useful in both ancient and modern times. They are typically hard, chemically non-reactive, and often require heat to be produced or shaped, which is why they have been used for everything from ancient pottery to high-tech electronics and even aerospace components today. Ceramics are all around us. Let's talk about its crystal structures. Studying crystal structures and properties of ceramics is such an important topic, especially if you're interested in material science, engineering, or just curious about how things work. So, why study structures and properties of ceramics? Because ceramics are composed of at least two elements, and often more. The crystal structures are generally more complex than those of metals. So, first thing first, we need to understand that ceramics are not like metals, which are usually made up of just one or two elements. Ceramics are composed of at least two elements, be it metal and a non-metal. And of them, ceramics can contain more than two elements, which means the crystal structure are more complex. While metal atoms are usually arranged in relatively simple pattern, ceramics involve more intricate arrangement of atoms on dies, which gives them their unique properties. The atomic bonding in these materials ranges from purely ionic to totally covalent. For those ceramic materials for which atomic bonding is predominantly ionic, crystal structures may be thought of as being composed of electrically charged ions instead of atoms. The metallic ions or cations are positively charged because they given up probably third enough. Now, let's talk a bit about covalent bonding, which also plays a role in ceramics. In covalent bond atoms share electrons, rather than giving them up completely. This type of bonding can give ceramics other desirable properties like better strength and thermal stability. It is fascinating how the combination of ionic and covalent can lead to such diverse materials, from something as simple as porcelain plate to complex high-tech applications. So, why should we study this? Because understanding the structure and properties of ceramics, we can create better materials. We can develop ceramics that are lighter, stronger, and more heat resistant. We can design ceramics that are less likely to crack under stress or that can conduct electricity in new ways. In renewable energy systems, ceramic can play a role in things like batteries, fuel cells, and even solar panels. The possibilities are humongous. Now, at first glance, this might sound a bit technical. AX-type crystal structure. So, what exactly are AX-type crystal structures? Some of the common ceramic materials are those in which there are equal number of cations and anions. These are often referred to as AX compounds, where A denotes as cation and X are anion. There are several different crystal structures for AX compounds. Each is typically named after common materials that assume the particular structure. Since there are equal number of cations and anions, we can assert that the overall change is neutral, which leads to some very stable and predictable crystal structure. What makes this topic so fascinating, though, lies in these materials share the same basic ratio of cations and anions. They can form several different types of crystal structure depending on how ions arrange themselves. Rock salt structure. Perhaps most common AX crystal structure is a sodium chloride, NaCl, or rock salt. The coordination number for both cations and anions is 6, and therefore the cation and anion ratio is between approximately 0.414 and 0.732. Now, what makes rock salt our lesson for this slide? Well, first off, cations and anions, those positively charged and negatively charged ions we talked about before. In the case of sodium chloride, sodium is the cation and the chlorine is an anion. The unit cell for this crystal structure, figure from your right, is generated from an FCC arrangement of anions with one cation situated at the tube center and one at the center of each of the 12 tube edges. The key to this structure lies in coordination number, which is 6 for both cations and anions. Now, the coordination number basically tells us how many nearest neighbors each ion has. In rock salt structures, each sodium ion is surrounded by 6 chloride ions, as you can see on your screens. This arrangement forms a face-centered cubic (FCC) lattice, a fancy way of saying that ions are arranged in highly symmetric cubic-like pattern. But what actually important here is that this configuration provides maximum stability for the material. Let's take a closer look at the sodium chloride crystal structure, which is a bit different from the others we discussed. It might seem a little similar to other structure like body-centered cubic (BCC). Sodium chloride structure shows a unit cell for sodium chloride crystal structure. The coordination number is 8 for both ion types, and ions are located at each end of the corner of the tube, whereas the tube center is a single cation. Interchange of anions with cations and vice versa produces the same crystal structure. This is not PCC crystal structure because ions of two different kinds are involved. So, what exactly is sodium chloride structure? Well, in this arrangement, tells us how many neighboring ions each ion has. Is 8 for both sodium and chloride. This means that each sodium ion is surrounded by 8 chloride ions, and each chloride is surrounded by 8 sodium ions. This high coordination number is a key feature for this structure. This makes the material more stable in certain conditions. Zinc lens structure. A third AX structure is one of which the coordination number is 4. All anions are tetrahedrically coordinated. Sabihin, one atom is being surrounded by 4 atoms, shown in the figure. This is called zinc blende as or sphalerite structure, after the mineralogical term for zinc sulfide. A unit cell is presented in figure. All corners and face position of cubic cells are occupied by S atoms, whereas the Zn atoms filled interior tetrahedral position. An equivalent structure resulted if Zn and S atoms positions are reversed. Thus, each Zn atom is bonded to 4 S atoms, and vice versa. In simpler explanation, each zinc atom is bonded to 4 sulfur atoms, and each sulfur atom is bonded to 4 zinc atoms. This is called tetrahedral coordination, whereas the atoms form shape of tetrahedron, a pyramid with a triangular base. AMBNXP type crystal structure elements. It is also possible for ceramic compounds to have more one type of cations, or two types cations, presented by A and B. Their chemical formula may be designated as AMBNXP. Barium titanate, having both Va, 2 plus, and Ti, 4 plus cations fall into this classification. In structures, the formula is written as AmBnXp. A great example would be barium, barium titanate, where there are two types of cations. So, when we look at the table summarizing these crystal structures, we can see the key attributes like coordination numbers, type of ions, and common examples. So we'll be moving on to our problem solving.
Now, we proceed to problem solving. Ceramic density computation. It is possible to compute the theoretical density of crystalline ceramic material from unit cell data. Having formula of density is equal to n prime, which is the number of formula units within the unit cell, multiplied by the quantity of the summation of atomic weights of all cations in the formula units, plus the sum of the atomic weights of all anions in the formula unit over the unit cell volume, or the V sub C, multiplied by the Avogadro's number, which is equal to 6.023 times 10 raised to positive 23 formula units per mole. Next slide po. Problem made easy. Next slide. Our group provided ceramic density computation sample problem for sodium chloride. On the basis of crystal structure, compute the theoretical density for sodium chloride. A while ago, it was mentioned that one of the most common AX crystal structure is sodium chloride and is generated from a phase cubic center structure, or FCC. Solution. The theoretical density may be determined using equation 1 from the right, where N prime is the number of sodium chloride units per unit cell, is 4. Both sodium and chloride ions form FCC lattice. To solve the problem, first thing to do is to get all the values. Then, we know the molar mass of sodium is approximately equal to 22.99 grams per mole, and for chlorine, it is approximately equal to 35.45 grams per mole. Next slide po. To get the value of unit cell volume, or V sub C, since sodium chloride is crystallized in the FCC crystal structure, wherein the variable A, which refers to the length, is equal to the 2 multiplied by the quantity of ionic radii of sodium, that is 0.102 nanometer, plus the ionic radii of chlorine, which is 0.181 nanometer. Then raise it to 3 because it is known as volume. Next is by unit analysis. The ionic radii of both elements are in nanometer. So we have to convert it into centimeter. That's why we can see it that it was multiplied by 10 raised to negative 7. After that, we already have the value for Avogadro's number since it is constant volume. After getting all the required values, we can now calculate it by substitute our values in the given formula. So density is equal to 4 times quantity of 22.99 plus 35.45 over 2 times 0.102 times 10 raised to negative 7 plus 2 times 0.181 times 10 raised to negative 7 times 6.022 times 10 raised to 23. So after none, we can now come up into theoretical density for sodium chloride, which equals to 2.14 gram per cubic centimeter.
To further understand ceramic, let us dissect its properties. The first notable mechanical property of ceramics is its hardness. Ceramics are hard hard materials that can often be harder than metal typically used. This stems from its strong ionic and covalent bonds between its atoms, which make it perfect for being an abrasive resistant material. Next slide, please. In strength, ceramics exhibit high compressive strength, meaning they can withstand significant compressing forces before breaking. On the other hand, they are also brittle, meaning they can fracture easily under sudden impact or stress. This brittleness is a consequence of the rigid crystal structures, which don't easily accommodate for deformation. Next slide, please. For fracture toughness, ceramics break quickly. Tension at room temperature without undergoing any plastic deformation. This fast fracture happens due to rapid initiation of growth of cracks. Despite their strong bonding, ceramics have low fracture toughness, about 50 times lower than metals, making them prone to cracking. Because of its low fracture toughness, ceramics are typically loaded in compression, where they are much stronger, with compressive strengths around 10 times greater than their tensile strengths. Next slide, please. Now for the chemical properties of ceramics. Ceramics have high chemical resistance because they are chemically inert, making them perfect for use in harsh settings such as chemical reactors, pipelines, and tanks. Unlike many metals that corrode or oxidize under comparable circumstances, ceramics are resistant to corrosion from acids, alkali, and salts, making them suitable for industries that handle large amount of harmful chemicals. Next slide, please. And also, ceramics can play a role in biocompatibility. This is because certain ceramics like zirconia and alumina are biocompatible, which allow for their safe implantation in the human body. This characteristic of ceramics are being used in bone replacement, dental implants, and other medical equipments.
Moving on to thermal insulation and their thermal properties, ceramics are widely known for their thermal resilience. Let's delve into the role as thermal insulators, where materials like alumina and zirconia excel due to low thermal conductivity. These materials effectively serve as barriers in high-temperature environments, protecting components in industrial and aeronautical applications, such as heat shields and engine exhausts. Next slide, please. Beyond thermal insulation, ceramics must also endure abrupt temperature changes without failing. This brings us to the concept of thermal shock resistance. While ceramics can often be sensitive to sudden temperature shifts, causing potential fractures, some have exceptional thermal shock resistance. Ceramics with finely grained structures can withstand these rapid changes, making them ideal for applications like cookware and turbine blades. Next, now let's ex- let's explore ceramic electrical properties where they offer unique advantages, starting with electrical insulation. Ceramics are typically outstanding electrical insulators due to their tightly bound electrons, which restrict the flow of electric current. This property is invaluable in electrical applications where ceramic serves as insulators in components like wires, cables, and circuit boards. Next, some ceramics, however, exhibit fascinating properties when exposed to mechanical stress. This leads us to piezoelectricity. Among certain ceramics, lead zirconate titanium stands out for its piezoelectric properties, generating electric charge under mechanical stress. This attribute is widely used in consumer electronics, telecommunications, and medical equipment for sensors, actuators, and transducers. Next. Additionally, certain ceramics display semiconductor properties crucial for high-performance electronics. Materials like zinc oxide and silicon carbide behave like semiconductors. Silicon carbide, for example, has a wide band gap and excellent thermal conductivity, making it ideal for applications in power electronics, LEDs, and high-temperature conductors.
Classification of ceramics. Traditional ceramics includes pottery, bricks, tiles, and porcelain. These are typically made from clay and are widely used in construction and household items. Next is the advanced ceramics. These materials have superior properties and are engineered for specific applications. Examples include silicon carbide and zirconia, often used in electronics and aerospace. Last is the glass ceramics. These materials combine properties of glass and ceramics, offering unique characteristics such as thermal stability and resistance to thermal shock. Next. Application of ceramics. Construction materials. Ceramics are used for brick and tiles. Durable and aesthetically pleasing, used in walls and flooring. Next is cements, essential for mortar and concrete in masonry projects. Sanitary ware, toilets, sinks, and bathtubs made from ceramic materials for hygiene and durability. Roofing materials, ceramic shingles provide insulation and weather resistance. Next slide. Industrial applications. For cutting tools, advanced ceramics like alumina are used in grinding wheels due to their hardness. Abrasives. Silicon carbide is utilized for polishing and grinding applications. Next. Medical applications. Bioceramics. Used in dental implants and prosthetics for their biocompatibility. Surgical instruments. Durable ceramic tools that resist corrosion. Next. Aerospace and defense. Ceramic armor. Lightweight materials provide ballistic protection for military applications. Engine components. High temperature ceramics are crucial in jet engines. Slide.
Now, let's talk about the common types of ceramics. First on the list is porcelain. Porcelain is a high quality type of ceramic material known for its strength, durability, and a smooth white surface. It is made from refined clay which is fired at high temperatures to achieve its glass-like non-porous structure. Porcelain is used for various applications, including tableware, tiles, and decorative objects due to its resistance to moisture and heat. Its fine texture and translucency set it apart from other ceramics, giving it a more elegant and delicate appearance. Next slide, please. Earthenware. It is a type of ceramic made from naturally occurring clay that is fired at relatively low temperatures. It is porous and absorbs water unless it is glazed that provides a waterproof surface. Due to its lower firing temperature, earthenware tends to be less durable and softer than stoneware or porcelain. It has used it has been used historically for pottery and other functional or decorative items across many cultures. Next slide, please. The third is the stoneware. Stoneware is type of durable and non-porous ceramic material fired at high temperatures, typically between 1,200 degrees Celsius and 1,300 degrees Celsius. It is known for its strength and chip resistance that makes it ideal for both functional and decorative purposes. Stoneware has a distinctive, dense texture and can have a natural and earthy appearance or be glazed for a more refined finish. Next slide, please. And the last one is the bone china. Bone china is a type of ceramic known for its high level of whiteness and strength. It is made by combining bone ash, feldspar, and kaolin clay, with the bone ash typically derived from animal bones. This type of bone china is fired at a lower temperature compared to other porcelain that gives it a delicate yet durable quality. Bone china is a highly valued for its fine texture and is often used for high-end tableware and decorative pieces. Next slide, please.
The next part will be the manufacturing process of ceramics. Manufacturing ceramics requires precision and expertise at every stage, including forming, firing, and glazing. Quality control is essential to ensure the final product's quality and durability. Ceramics offer versatility and durability, making them an excellent choice for kitchenware, building materials, and biomedical implants. This guide provides an overview of how ceramics are manufactured on a large scale. Thanks. First, raw material procurement. The procurement of raw materials is the first step in ceramic manufacturing. Raw materials are transported and stored at the manufacturing facility. Ceramics are made from moderately impure clay materials extracted from natural sources to extremely pure powders created through chemical synthesis. They are produced from silica, sand, quartz, feldspar, and aluminosilicate. These raw materials enhance ceramic properties such as abrasion resistance, and electrical resistance. The second stage will be beneficiation. Chemically synthesized ceramic powders also require beneficiation. This step focuses on the techniques used to refine naturally available raw materials. Before being transferred to a ceramic manufacturing facility, naturally occurring raw materials are frequently subjected to some beneficiation at the mining site or an intermediate processing facility. These processes help to eliminate undesirable impurities and ensure a steady supply of raw materials of the required purity. Next slide, please. As for the third stage, we have mixing. Mixing is used to blend ceramic powder components to create a more uniform material for chemical and physical shaping. Ceramic materials are frequently mixed in pug mills. During the mixing stage, the ceramic mixture may have several processing aids added. Binders and plasticizers make dry powder and plastics. The flocculants, surfactants, and anti-foaming agents are added to slurry processing to facilitate processing. Processing of plastics and slurry also uses liquids. Fourth stage will be forming. There are many forms of ceramics, but one example is a slip casting. Here, a plaster mold is filled with slip or liquid clay. The water is drawn out of the plaster mold walls, leaving a layer of solid clay inside. Firm clay can be removed once dried. These techniques rely on organic additions to the ceramic mix to shape the material into the desired form. The specific forming technique depends on the ceramic product's manufacturing type and application. Next slide, please. The fifth stage will be green machining ceramics. Grain machining refers to the process of shaping a ceramic part while it is still in its green or unsintered state. The grain machining process covers clamping and handling techniques suitable for ceramics and applying ultra-hard, high-performance cutting materials. Grain machining allows for the creation of complex shapes and features that may not be possible using traditional forming techniques. It also allows for higher tolerance and higher precision in the final product. Sixth stage will be drying. Drying is used to remove the water added to the clay during the forming step. This water must be removed before firing or sintering the ceramic part. The drying process must be carefully controlled to ensure that the ceramic part dries evenly at a rate that prevents cracks and other defects. The drying rate depends on material characteristics, processing variables, and other factors that influence water and vapor migration rates from the internal areas of the formed part to the dry atmosphere. The last but not the least stage is, next slide please. Okay, second to the last stage will be thermal process. Ceramics thermal process generally involves high temperatures and results in high resistant materials. One necessary thermal process is firing, which involves placing formed and glazed greenware in a sintering oven for heat treatment. As a result of sintering, the material becomes dense and hardened to the final state. After firing, the ceramic part has achieved its final properties and is ready for final processing and packaging. The eighth step will be glazing. Glazing involves applying a liquid glaze coating to the ceramic part surface. The glaze can be applied by brushing, pouring, or spraying. The glaze serves several purposes in the ceramic manufacturing process. First, it can enhance the appearance of the ceramic part by adding color or texture. Second, it can also improve the durability of the ceramic part by making it more resistant to wear and tear. Third, in addition, the glaze can make the ceramic part more resistant to water and other liquids by creating a non-porous surface. Next, glaze firing. During this step, the glazed ceramic part is loaded into a kiln and fired at a high temperature. The kiln is slowly brought to the appropriate temperature for the silica and the glaze to melt, then slowly cooled again. This process causes the glaze to fuse to the surface of the ceramic part, creating a hard, glass-like coating. The tenth step, or the tenth stage rather, is the final processing and packing. After the glaze firing system, the ceramic part undergoes final processing and packaging. Final processing includes additional machining or finishing operations to achieve the desired shape and surface finish. It may also involve additional steps to finish the product, such as polishing or painting. After final processing, the ceramic part is ready for packaging. Packaging includes wrapping the ceramic part in protective materials and placing it in a box or container ready for shipping. Next. So to end our presentation, we would like to conclude with ceramics have a rich history and a bright future. Their unique properties, ranging from strength and durability to electrical and thermal insulation, make them essential in a wide variety of applications. As technology continues to advance, the demand for advanced ceramics is likely to grow, leading to innovate materials and products that will shape our world in the years to come. This concludes our presentation. Thank you everyone for listening and have a great day ahead.